Hi everyone, welcome to this dedicated session on Wi-Fi migration. I'm Charlotte Desmoulins, Digital Content and Growth Manager for the Network Business Division, and I will be your host for today's session. Before we start, always few reminders. This webinar is recorded, so if that may be an issue for you, we encourage you to disconnect now. Obviously, all your lines are on mute for the presentation, but we can take all your questions on the panel, so don't hesitate throughout the webinar to ask them, and we'll take a time at the end to take them. And of course, the presentation will be available. Today, our speaker is Patricio Martelo, Solution Architect Director. Hello, Patricio, how are you? I heard you prepare a special interactive session today, multiple polls. So please, attendees, share your feedback. There is no right or wrong answer. So go ahead. Floor is yours, Patricio.
Hello, Charlotte. Thanks for the introduction. And yes, this will be an interactive session. There will be multiple polls throughout this presentation. So by all means, please participate. There's no right or wrong answer, and that will help us get the pulse of this session, and that will make it much more interesting. So without further ado, if you're planning a Wi-Fi migration and want to know how to go about it from a technical standpoint, this is the webinar for you. I share with you all insights to keep in mind from a design perspective to avoid getting stuck at 6s and 7s and to make a stellar performance instead. So what's the motivation for this webinar? The typical network depreciation period is 5 years, which means about 20% of networks are refreshed every year. Of course, that some customers refresh more or less often. But this year in particular, more than 50% of customers are considering a migration towards Wi-Fi 6E or 7, which come with a new set of challenges such as the 6 gig band, WPA3, and others. The market is also evolving. Some customers are finding that their current network vendor roadmap does not align with their own vision and strategy from a deployment model point of view, such as cloud versus on-prem, or from a subscription and licensing perspective, or due to vendor mergers and acquisitions. As such, more and more customers want to migrate to omni-access Stellar Wi-Fi and want to know how to plan for this migration. In this webinar, I will be covering the various considerations that you need to keep in mind for a successful migration. These are general principles which will be applicable no matter which solution you're migrating from. There will be various polls throughout this webinar, as I said, and so you can either go to menti.com and enter the code that you see on the screen, or you can scan the QR code with your phone, and at various points, you will be asked to provide your inputs. So with that, here's the agenda. There'll be an introduction where I will specifically set the scope for this session. Then we'll delve into the specificities of the 6 gig band. With that, we can start to consider the challenges from a planning perspective. We'll continue with the considerations on the wired network, VLANs, subnets, PoE, speeds and feeds, followed by network admission control. The new requirements for encryption on the 6 gig band, that's WPA3, simultaneous authentication of equals, enhanced open, some considerations related to EduRAM. We continue with SSID planning strategies, wireless intrusion prevention, and a very simple demonstrations and takeaways. So without further ado, let's begin. There's been other webinars in which we have covered all the improvements in the Wi-Fi 7 specification. I will not be going through those today. What I will be focusing on is how to design for a migration to Wi-Fi 6E or 7 today with the APs that are available today. As I'm running this webinar for different regions, I will be covering both the European and US regulations. The vast majority of countries have adopted regulations that resemble one of these. Let's start. The first big topic is the 6 gig band, and it's time for our first poll. So you can go to the website menti.com and enter the code, or scan the QR code with your phone. And here there's two questions. The first one, the question is, what is your experience with the 6 gig band? Specifically in an enterprise space. So the question is, who has already deployed the 6 gig network, whether it's 6E or 7, and who hasn't done that yet? So I'll give you a bit of time for the answers to come through. Some answers are already coming. I see lots of people who have not deployed it yet. In fact, nobody has deployed it yet. And that's good news because this webinar is good for you. So we'll move on. That's good to know. So back to the presentation. All right. The 6 gig band. Whether we are talking about Wi-Fi 6E or Wi-Fi 7, the real game changer is the new 6 gig band, which opens up a lot of new spectrum for Wi-Fi. Now, this band is not the same all over the world. In the US and in countries that mimic the FCC regulations, it opens up a massive 1200 megahertz of spectrum. That is more than double what is available on the 5 gig band. In other places, such as the European Union, which adopt ETSI regulations, we have less, 500 megahertz, and roughly about the same amount of spectrum that we have on the 5 gig band. So it's now time for our second poll. And the question is, compared to the 5 gig band, how many channels does the 6 gig band provide? The possible answers are, first, about the same number of channels, and the second, more than double the number of channels. So let's see if the answers are already coming through. So we have a few answers. And so for most of you, the answer seems to be that it's more than double the number of channels. And in fact, this is a trick question. This is a trick question because the answer depends on the regulatory domain. In Europe, it is about the same number of channels, but in the US, it's more than double. So depending on where you are at, the answer is different for you. All right, so let's go back to the presentation. So how many channels do we have? To start, I think we all know that in the 2.4 band, there's only 3 non-overlapping channels. On the 5 gig band, in the US there's 25 and in Europe there's 23. These numbers may vary slightly because some channels have some restrictions on power, etc. And you may use them or not depending on that. Now, how about the 6 gig band? There's 59 channels in the US and 24 channels in Europe. So we can see that in the US, we have more 80 megahertz channels on the 6 gig band than we have 40 megahertz channels on the 5 gig band. That is something we can definitely take advantage of in our designs. But in Europe, on the other hand, there's 24 channels, about the same number as in the 5 gig band. But let's not feel discouraged about that because we are still getting an entirely new band, which not only is new, but it is, at least for now, almost pristine and it is contiguous, unlike the 5 gig band, which is very polluted and has a gap in the middle. Here we see an experiment that I did at home when I got my first 6E card. At the top, we see the spectrum analysis of the 2.4 band, and no surprise, it's completely congested. So many networks that we cannot even read their name. It's like the I-5 highway in California, completely congested. In the middle, there's a 5 gig band, still completely congested, and we cannot even make out what those networks are. On top of this, there's a gap, which makes it difficult to use wider channels. But look at the bottom of the screen. This is the 6 gig band. At first, I thought my card was not working, or the drivers were not the right ones. I could not believe that there was nobody on this band. So The next day, I took the card to the lab and I turned on one of my stellar access points, and sure enough, the card did work. It's time for our next poll. As a network designer, one of the first questions we need to answer very early on is how many access points we need. I will tackle this question right after this poll. So let's get to it. Let me switch to the next question. And there we are. So the question is, enabling the 6 gig band will require, and then there's a few different answers. So you can select actually multiple answers for this question, and it can be about the same number. You may need a few more access points, or it may depend on materials, or it may depend on your current design, or maybe it depends on the channel width. So what do you guys think? And so we have a nice distribution of answers. And again, there's multiple answers to this question. And it's quite interesting to see that you have selected all possible answers, and that is correct. In fact, all answers are correct. It depends on the context. So let's look at that. Back to the presentation. So it's time to have some fun with decibels. Let's examine, to start to answer this question, we will first examine the free space path loss. We have the formula, which is a constant plus the sum of logarithms, and it depends on the distance and the frequency. The higher the frequency, the higher the loss. How much higher? In the US, if we compare the top of the 6 gig band with the bottom of the 5 gig band, there's about 3 dB of extra free space path loss. In Europe, the difference is about 2 dB because we don't have the entire band. What this means is that right off the bat, all other things being equal, and that includes the channel width, we will need a little bit more EIRP to achieve similar signal to noise ratio. So we can go and check our current EIRP levels to see how much margin we have. Assuming we keep the same channel width, we will need about 3 dB more in the US and about 2 dB more in Europe. But free space path loss is not the only consideration. There's also material absorption. Is it the same on the 5 gig band as it is on the 6 gig band? For some materials like drywall, it is about the same. But for other materials like brick, it can be much more, about 5 dB more. Now, we can already draw some conclusions from this. If the current design is capacity-based, the existing APs will be far from their maximum ERRP, and there will be ample margin. The APs will be placed inside rooms as opposed to being placed in corridors. Think about a hotel, for example. So it is likely we will be able to just replace the existing access points with newer ones to achieve an equivalent coverage. That is with some conditions. For example, same channel width. We will examine this later, so bear with me. If, on the other hand, the design was coverage-based, the APs may be closer to their maximum EIRPs. They may be sparsely deployed in corridors as opposed to inside each room. And in that case, we may not have enough margin to increase the ERP to compensate for the extra free space path loss and the extra absorption in the material. So that may require a new plan, or in the worst case, a redesign. Here we have a wireless planning done on eCahau at 5 GHz compared to 6 GHz. So 5 gig at the top, 6 gig at the bottom. For 5 GHz, we use the AP1311, and we need 16 of them, transmitting at 18 dBm. For 6 GHz, we use the AP1411, and we still need 16 of them, but at 21 dBm. Now note that the coverage is almost identical, except for a few holes. If these locations are important and we absolutely want the 6 gig coverage there, we may need to deploy a few extra APs. but otherwise we can still fall back to 5 gig coverage. The next question is the channel width. Intuitively, we know that wider channels can give more throughput, and knowing we have more bandwidth up to 1200 megahertz in the US, we may be tempted to go with the widest channels possible. However, it is a little bit more complex than that. Let's talk about power limits on the 6 gig band. In Europe, the limit is the same as in the 5 gig band. It is identical for AP to client and client to AP. It's 23 dBm, which is equivalent to 200 milliwatts. There's also a power spectral density limit of 10 dBm per megahertz. However, this limit is a bit meaningless in Europe, and we will see why in a minute. In the US, on the other hand, these limits are not identical. The IP can transmit up to 30 dBm, that is 1 watt, whereas the client can go up to 24 dBm, that is about 250 milliwatts. There is a power spectral density limit of 5 dBm per megahertz in the case of the IP and minus 1 dBm per megahertz in the case of the client. We'll see in the next slide that unlike what happens in Europe, in the US, those are the real limits. So let me illustrate that. This chart shows power limits in total ERRP and also in PSD in US and Europe for low power indoor devices. On the right, we see that in Europe, these limits are the same for AP and client. Furthermore, the ERP limit is 23 dBm. There's also a PSD limit of 10 dBm per megahertz. But if you do the math, at 20 megahertz, 10 dBm per megahertz already gives 23 dBm, which means that in Europe, no matter what the channel width is, the ERP limit is already 23 dBm or 200 milliwatts. In the US, there's 5 dBm limit per megahertz. If you do the math, you see that this gives 18 dBm at 20 megahertz, 21 dBm at 40 megahertz, 24 dBm at 80 megahertz, and so on. And why is that? Because the wider the channel, the more noise there is, and the more ERP you need to maintain a similar signal-to-noise ratio. We should also note that the limit for the client are always 6 dB below the access point, whether in terms of PSD or ERP. So the limit of 30 dBm in the US is only applicable for a channel width of 320 MHz and only from the access point to the client. Are you confused yet? What channel width should you use? To wrap this all up, in the US, the limiting factor is the PSD. There's 59 20 MHz channels, there's a 3 dB extra free space path loss, and we need an extra 3 dB every time the channel width doubles. So using wider channels is quite likely. Not only there's more channels and more bandwidth, but using wider channels allows for higher power, which is beneficial especially for the clients as they have a lower limit. You will likely be using 40 or 80 MHz channels depending on the type of deployment, and on Stellar, 80 MHz is the default. In Europe, on the other hand, there's 24 channels. We have an extra 2 dB of free space path loss, and we still need 3 dB extra every time we double the channel width. If the current access points have enough margin, we can replace them and increase the channel width. Wider channels are possible, but less likely because we don't have more channels on the 6 gig band compared to the 5 gig band. So you will likely be using 20 MHz or 40 MHz. The default on Stellar is 80 MHz, so you may need to fine-tune the RF profile to change it to 20 or 40 according to your needs. So let's wrap up this section with some key takeaways. AP swap like for like is possible, especially if your current design is capacity based, but it is unlikely if your current design is coverage based. A few extra access points may be required, and this comes with conditions such as the channel width. You should check your current ERP levels to see what's your margin for maneuver. And don't forget to consider your building materials, as absorption can vary significantly between bands. The next session is channel discovery and roaming. Clients need to discover channels being used to connect and roam between access points. On the 5 gig band, this can be done actively or passively. The roaming decision is done by the client and it can be influenced but not really controlled by the network. That can lead to some well-known issues such as the sticky client problem. The question is, can we improve this on the 6 gig band? The answer is yes. This changes on the 6 gig band, simply because there's more channels and it would take longer to scan them. While the client is scanning channels, it's not forwarding traffic, and at the same time, that can impact battery life for the client. So, on the 6 gig band, there's been several changes. One of the big changes is the use of preferential scanning channels for active scanning. That is, 1 in every 4 channels. This saves scanning time. But another change is the introduction of out-of-band scanning. In particular, the reduced network report provides a list of adjacent access points even on other bands. What this means is that a client that is listening on the 5 gig band can be informed of channels being used on the 6 gig band. As a designer, this means that even if one day all clients support the 6 gig band, which is not the case today, we may still want to keep the 5 gig band active to assist clients in associating to or roaming between 6 gig access points. I can tell you that some clients do not see the 6 gig band unless the 5 gig band is also enabled. So they either don't see it or they take a very long time to connect to it. So as a designer, again, one of the recommendations would be to plan to keep the 5 gig band active. The next item is how are we going to plan the migration? How are we going to split it in phases? From a Wi-Fi plan point of view, we can never go wrong with a new plan. However, as I have mentioned already, APs are designed to be one-to-one swappable with some considerations. Using the old plan will depend, as I already mentioned, on whether that plan was capacity-based or coverage-based. So it could be a good fit if it was capacity-based, but probably not if it was coverage-based. We can check the current ERP levels to see how much wiggle room there is. And we should consider, as I explained, that 6 gig requires extra dBs for free space path loss, absorption, and also if we are planning to increase channel width. As for splitting the migration in phases, the first option, which is pop and swap APs almost randomly as we go, is a terrible idea. And this is because the old and the new solution have different control planes. So there's no coordination whatsoever between them. No coordination of channels, power, roaming, nothing. So the right way is divide and conquer. Phases should be planned according to the natural RF boundaries. A natural RF boundary could be buildings, floors, elevator shafts, staircases, anywhere where the coverage would normally drop and no seamless roaming is expected even with a single solution. To help in this migration, we have introduced a third-party compatible mounting kit that can replace existing ones without drilling new holes. So this helps from an installation time and cost point of view. You can simply pop this one and just reuse the existing holes. Let's now examine the considerations on the access layer. Specifically, PoE requirements, speeds and feeds, as well as VLANs, subnets, and DHCP. And we have a new poll coming up. So let me change to the new one. So the question is, to unlock the power of Wi-Fi 7, we will need, and you have to choose one, PoE, PoE Plus, PoE Plus Plus, or DC power supplies. What do you guys think? So most of you think that PoE Plus is sufficient, while some of you think that you do need PoE Plus Plus. Okay, we got a few answers. It's getting even between those two. Nobody thinks that this can work with 802.3AF or that we require DC power supplies, which is good. All right, let's go back to the presentation. All right, so PoE. Enabling the 6 gig band means more radios and more spatial streams. There's also, let's not forget that there's also the 2.4 and 5 gig radios. There's, for some APs, a scanning radio. There's BLE or ZigBee IoT radios, as well as USB and network ports. So it's easy to see why the new access points consume more power. 802.3bt PoE, that is HPOE or PoE++, is highly recommended, although the Wi-Fi 7 access points are retro-compatible with limitations with PoE Plus or 802.3AT. In some cases, they can work with dual feeds, although this is costly from a wiring point of view. One question you may have with a push to environmental sustainability is whether you can switch off some of the other radios to save power. Maybe. You do need to consider all the devices that do not support the 5 gig band yet. And as I said before, you also need to consider how channel discovery works. So you may want to keep the 5 gig band if you have some coverage gaps on the 6 gig band, but you may also need to keep it to assist clients in associating to and roaming between 6 gig radios. One key takeaway is that in order to benefit from Wi-Fi 6E and or 7 in general, you will need to refresh the access layer with HPOE 802.3bt switches, except if you're only planning to use the entry-level access points, because those access points can work with 802.3AT. For the mid-range access points, even though they can work with 802.3AT, to get the maximum performance out of them, you do need to have 802.3 BT PoE. So one takeaway is that in general, to benefit from the performance of Wi-Fi 6E and 7, you will need to have 802.3 BT PoE. There's another poll. So we already discussed PoE. What about bandwidth? What about speeds? So let me switch the question. And the question is, to unlock, actually, there we go. To unlock the power of Wi-Fi 7, we will need, and you need to choose one, 50 gig ports, 10 gig ports, 5 gig ports, 2.5 gig ports, or maybe 1 gig is enough. And so we have quite a nice distribution of answers. Looks like a majority thinks 5 gig ports is required. Some people think it's 2.5. Some people think it's 10. One person thought it's 50. And one person also thinks that 1 gig is sufficient. Okay, very interesting. Let's analyze that. So back to the presentation. Now, we have already established that we will need HPOE, 803BT. In most cases, to take full advantage of these access points. But how about the port speed? If we look at the marketing material, we may think that we need 50 gigabits per second ports. We know we don't have PoE on such port, but the question is, do we need 10, 5, 2.5, or maybe 1 gigabit is just fine? The first thing to understand is that what we see on the left-hand side is data rate. That's the speed over the air, which is different from throughput, which is the speed on the wire. But even then, those figures are simply what the standard allows. But no AP from any vendor can deliver those today. Because to achieve those values, that would require not only 320 MHz channels, but also 16 special streams and 4096 QAM modulation. No AP in the market supports 16 special streams. On top of that, in Europe, there's only one 320 MHz channel. So that is only possible for residential use, but not for enterprise use. Moreover, 4096 QAM modulation is possible, but that requires a really good signal-to-noise ratio, which means you have to be very close to the access point. And that's just for the data rate. Data rate, as I said, is not the same as throughput. And why? Well, because Wi-Fi is shared media. It's half duplex. And there is a lot of overhead due to contention for media access. What's more, not all clients are Wi-Fi 7 enabled, and they won't be for a long time. And there's always a bottleneck in the WAN. So the real world throughput is much, much less. We have already established that HPOE will be required, and if you look at the specs, you will notice that HPOE ports can deliver at least 2.5 gigabits per second. So the question is that enough? For the majority of use cases, it is. There will be some which can push this beyond 2.5. For example, use cases involving MLO backhaul for mesh. Don't get me wrong, as a switching vendor, if all customers buy 10 gig ports, that will make our sales reps very happy. But as an engineer, if your access layer supports 5 gig or even 2.5 gig, that's quite adequate for Wi-Fi 7. You don't necessarily have to wait until you can refresh it all with 10 gig. 1 gig is not enough because there's free radios, but when you get a PoE++ port, you are already getting at least 2.5 gigabits per second. Moving up on the OSI model, let's now consider VLANs, subnets, and DHCP. APs can be deployed in bridge mode, which is the case of Stellar APs, but also Aruba Instant Access Points and others. Or they can be deployed in tunnel mode when using controllers. This choice has an impact because in the first case, the client VLANs are just access layer VLANs, whereas in the second case, those are data center VLANs. So in the first case, we will require a set of VLANs and subnets that go with those VLANs at the access layer on top of the AP management VLAN. Whereas in the second case, there's only one VLAN for the AP and the client traffic is tunneled and uses DC VLANs and subnets. For the AP management VLAN, we use different options to help the AP discover its management server or controller. OmniAccess Stellar uses option 138, whereas other solutions use option 43. The question is, when migrating to OmniAccess Stellar from a controller-based solution, can we do so without changing our VLANs and subnets? The answer is yes, and for that, we also need to tunnel traffic. We do that without a controller. We can tunnel traffic to a switch. This slide illustrates some of the use cases for tunneling. Firstly, there's guest tunneling. This is always recommended, and it consists in tunneling all guest traffic to one or more guest tunneling termination switches located in the DMZ. This keeps guest traffic isolated from corporate traffic. The other use case shown on this slide is useful when migrating from another wireless solution which uses controllers, which are typically deployed in the data center. In this scenario, Swapping those controllers with guest tunneling termination switches allows us to keep using the same VLANs and subnets without adding new access VLANs and subnets in the campus. Note that this is not necessarily something that we recommend in general, but only to those customers who do not want to add access layer VLANs and subnets. Another use case is shown on this slide. Here, company policy requires all traffic to be analyzed by centralized security appliances deployed into data centers. This is achieved by tunneling all traffic from access points to the tunneling switch deployed at the data center sites. And in this example, this is done in a highly available redundancy scheme that can even withstand the failure of an entire data center. For further details on this architecture, you can refer to an application note and video that you'll find on our Spacewalkers technical community. Moving on to network admission control. Typical enterprise use cases include employee, BYOD, guest, and IoT. For employee access, we may typically use either 2-to-1x back to Active Directory. For some more advanced features such as host integrity checking, we may have Aruba ClearPass or Cisco ISE in conjunction with Active Directory. This is similar for BYOD use cases. For guest, we may use one of those options or a more specific one such as Ucopia. And for IoT, we may do something similar and also some specific options depending on the IoT vendor. But the point is, in enterprise deployments, authentication databases are external to the Wi-Fi solution. And so when migrating to Omni-Access Stellar, we can keep it that way. And no change to client devices will be required. We do not necessarily need to migrate our NAC to OmniVista UPAM. To that end, we have some application notes and video tutorials that explain how to configure all that using Aruba ClearPass or Cisco ISE or Ucopia or Microsoft Active Directory. So you can check these out, and of course you will find them on Spacewalkers. Moving on to encryption. Now, I'm not going to go into the details of WPA3 and Enhanced Open because these are topics that we have covered in the past, and we have some great webinars by Jorge Arasans on that. But you should know that in order to use the 6 gig band, WPA3 and or Enhanced Open or Opportunistic Wireless Encryption become mandatory. Now, in most cases, the existing SSIDs will be using WPA2 for employee, BYOD, and IoT, and just plain open for guest. So, can we keep using the same SSIDs? What if clients don't support WPA3 or Enhanced Open? Let's start with WPA3 Personal. To make a long story short, WPA3 replaces pre-shared keys with passphrases and uses simultaneous authentication of equals. This protects from brute force dictionary attacks. It is mandatory on the 6 gig band, but optional on the other bands. There is a mode called transition mode, which is backwards compatible with WPA2 and allows a smooth transition from WPA2 to WPA3 on your existing SIDs. This, however, may cause problems with some clients with old drivers that do not associate to an SSID if the beacon includes an option that they don't understand. So we recommend testing this option in a small AP group in case your network includes some of those more touchy devices, such as wireless barcode scanners. On the slide, I have highlighted in bold the naming that we give to these modes on the OmniVista interface. Now for WPA3 Enterprise. As a reminder, WPA2 Enterprise does not use pre-shared keys, and so it was not susceptible to brute force attacks. What WPA3 does, however, is add protection for management frames, which is also done for personal, even though I didn't mention it. If you think about it, it is crazy that management frames have not been protected for such a long time. The transition mode consists simply in making management frame protection optional for those clients that don't support it. There's also a Suite B mode or 192-bit mode, which is for government and defense. As a takeaway, transition mode usually works fine because these devices are normally not IoT devices, but user devices that run an operating system such as Windows, Android, or iOS and have updated drivers that do support these options. Finally, for guest access, there's Enhanced Open, which adds encryption even on open SSIDs. There is no change in user experience. There is no need for a passphrase. And it is mandatory on the 6 gig band. The question is, how can we plan our SSID strategies in a brownfield scenario, knowing that we will have some existing SSIDs, some devices that may not support WPA3, etc. A typical scenario looks like what we have on the left-hand side. We have WPA3 Enterprise using certificates, that is TLS for employees. Then we have WPA2 Enterprise using PEEP, TTLS, or TLS for BYOD. For IoT, we have WPA2 Personal with pre-shared keys, and for guests, we have Open. We cannot keep these settings on the 6 gig band. They are not allowed. So we can create new SSIDs for the 6 gig band where we enable WPA3 and or Enhanced Open. We can enable these new SSIDs on the other bands also. On the old infrastructure, it is still desirable to enable WPA3 in transition mode for enhanced security. Before doing that on a large scale, we should try it out in a reduced AP group and with the key IoT devices because, as I said before, some IoT devices with all drivers may not like it. But for the other devices, this works fine in most cases. In this slide, I have given examples for all 4 use cases. However, at least for now, there's hardly any IoT devices supporting 6 gig, and you may not really care about supporting 6 gig for guest access. One thing to note is that there is nothing on the OmniVista GUI that is called transition mode. This is achieved by making management frame protection optional, and that is only possible on SSIDs that are not broadcasting on the 6 gig band. The other point is that, as you probably realize already, new SSIDs will require intervention on client devices. One question is about EduRoam. On EduRoam, we use a single SSID. We cannot use multiple SSIDs. So for that reason, transition mode is not possible for EduRoam. And so we have to use a single EduRoam SSID, and therefore we need to enable pure WPA3 Enterprise across all bands. Now that will work for the vast majority of clients because EduRoam clients are not IoT devices. They are user devices running Windows, Mac, Android with updated drivers, and WPA3 has existed since 2018. So that will not cause issues for the vast majority of clients. We're almost reaching the end of this session, but there is one important point to highlight. When you have two autonomous wireless solutions broadcasting the same SSID, they will see each other as a rogue and do a denial of service on each other. And that is not good. To avoid that, you must whitelist solution B access points on solution A access points and the other way around. So that's it. But pay attention to this because that could severely impact your Wi-Fi deployment. So the last section is a very, very simple demonstration. We have this simple scenario in which we are migrating from an OmniVista 2500 on-prem deployment to an OmniVista 10 in the cloud deployment. This example is illustrating a migration which is halfway done. We have two parts of the network. One is running on the old infrastructure and the other one is running on the new infrastructure. Authentication is external using Active Directory MPS. We have two SSIDs, one WPA3 Enterprise and another one which is WPA3 Personal for IoT. We have already enabled transition mode on the old infrastructure and have established that all our client devices tolerate it well. We are simulating a user and IoT device roaming from the old to the new network, and we simulate that by shutting down the radios on the AP either on the left or on the right-hand side. As we do that, the client associates to the AP on the right-hand side, which is broadcasting identical SIDs, which will place the user on the same VLAN and subnet, but this time on the 6 gig band and on pure WPA3. Because the user lands on the same VLAN and subnet, there is no change to the client AP. This migration is not, or this roaming in fact, is not totally seamless because these two networks have separate control planes. But this is representative of what happens when there's two different control planes, such as migrating from another vendor. In the video that I will show you, there's some minimal packet loss which you won't see on the video, as the video only shows the client perspective. But the point is, the point that the video is illustrating is that there's no change required on the client, and that roaming is as seamless as it can be when roaming between two different solutions. And here it is. Apologies for this being in French, as I took these videos with my phone. However, the numbers remain the same, even in French. On the left-hand side, we have the IoT SID with WPA3 Personal. In fact, this device is roaming from the new infrastructure back to the old one. And I'll play the video, and we see that it starts connected on the 6 gig band. And then as I switch off that radio, it will revert to the 5 gig band, which is running on the other access point. And there it is. Now, for the second video, I'm doing things the other way around. And this user is a WPA3 user. So for this one, it starts connected on the 5 gig band, which is on the access point on the left. And then it will roam over to the access point on the right and connect to the 6 gig band once I switch off the radio on the left-hand side access point. You probably noticed that at no point the connection was lost. That is not to say that there was no packet loss. There was a little bit of packet loss, but it's actually very, very good. So let's close with a wrap-up of all Wi-Fi migration tips. Number one, you can start creating an IoT inventory to assess the risk of migrating to WPA3. You know OmniVista helps you do that. You can enable WPA3 in transition mode in a small AP group and test how your devices react, particularly those more finicky IoT devices such as barcode scanners. You should plan your SID strategy accordingly. Plan your network migration in phases using a divide and conquer strategy and leveraging the natural RF boundaries for demarcation between old and new infrastructure. Swapping APs will work in most cases with some conditions, particularly if your existing design is a capacity-based one and if you maintain the same channel width. We have a mounting kit to help with that, but a few extra access points may be required in some corner cases. 802.3bt HPOE is highly recommended and may be required depending on the AP model. 802.3bt ports are 2.5 gigabits per second multi-gig or higher. 2.5 gigabits per second is recommended and affordable for investment protection. Sure, more is better, and it will future-proof your network for Wi-Fi 7, 8, 9, etc. But it's not strictly necessary or across the board. You can tunnel your traffic if you have for security policy or to keep using your existing user VLANs and subnets as they are. If you're using an external database for authentication and network admission control, you can keep doing this and it will avoid client device reconfiguration. You may need to fine-tune your RF profiles. I have not covered this, but you may need to pay attention to cell reduction techniques to avoid RF bleeding between old and new infrastructure. Finally, you will need to whitelist friendly access points to avoid denial of service because of wireless intrusion prevention. And with that, you're on to a Stellar migration. So I hope you find these tips useful, and I'd be happy to revisit this with you again next year. Thank you for your attention, and if you have questions, I will try to answer them. So Charlotte, do we have some questions?
Yes, indeed. Thank you for the presentation, Patricio, and those interactive polls. I hope the audience liked it. Okay, so one of the first question I have is there a way to simplify migration from OmniVista 2500 or OmniVista 4 to OmniVista 10?
Okay. Yes, so that is something that we're working on. If you're running the latest versions of OV Series 4 or OmniVista 2500, that will simplify the migration to OmniVista 10. That is not to say that that migration will be automatic, but it's something that our professional services team will be able to do for you.
Okay. I see people requesting for the presentation. It will be shared in the post communication via email. Don't worry about that. We will share the presentation with you guys.
And it should be posted on Spacewalkers as well,
Yeah,
right?
yeah, of course, and on Spacewalkers, of course. I have another one. Will 1 gigabit be enough for Wi-Fi 7? What are the real life speeds we can expect?
Okay, I think I did provide a lot of points on this question. In the industry, we have been talking about multi-gig for quite some time. The throughput that you get, it really depends on many factors, and I explain most of them, I think. But with Wi-Fi 7, we can see that really we can push things above 1 gigabit per second. So I don't think 1 gigabit port will be enough, because you can go well above 1 gigabit per second in a real life deployment with Wi-Fi 7. So the question is, as I said, because you will need HPOE to actually use at least the mid-range access points. You will need HPOE. With HPOE, you already get 2.5 gigabits per second. Yeah, because if you look at the switch specifications, any HPOE port gives you 2.5, if not more. So, in short, yes, you can definitely go above 1 gigabit per second. In some use cases, I mentioned MLO, I mentioned meshing, backhaul. You can go well above 2.5 gigabits per second. You can do 5 and even more. So as a general guideline, I don't think 1 gigabit per second will cut it.
Okay, thank you. I think that's it. You can close. I'll let you close with your words if you wish, Patricio. But thank you everyone for attending and obviously answering the polls and having an interactive session this morning.
Yes, so that's my message also. Thank you very much for your attention. Thank you very much for participating in the interactive polls. I hope you have enjoyed that. And if you did, then please let us know. It certainly makes our sessions more interesting for us as well, and hopefully for you also. So thank you very much, and see you next time.
Thank you very much. Have a good day, everyone. Bye bye.